Hello. This is what they call the infamous ladder problem from related rates in calculus. Take your time to read this question and see if you can note anything down. Okay, so let's begin by highlighting the important points in this question. So, looking at this question, we know that the ladder is 10 feet long and the bottom is sliding away from the wall, right? And what we're trying to find is by what distance or by what rate is the top of the ladder coming down when the bottom is a certain distance away, and that's 6 feet. Okay, to make sense of this, we're going to draw a triangle. Why? Because imagine the ladder is the hypotenuse of a right triangle that is formed in between the wall, the floor, and the ladder, right? So if you look at it that way, you can see that the ladder itself does not increase or decrease in rate, right? But the ladder, when it slides in the bottom, the top automatically comes down. Imagine a falling ladder, that is. So let's put all the details we have into this drawing that we make. The length of the ladder is 10 feet long. We have seen that. And the distance from the wall is 6 feet. We have put that already. And the rate at which the ladder is moving away is 1 foot per second, which would be your dx over dt. And here's an interesting fact for you. You know how our units are feet per second, right? Notice the bottom or the denominator of the units is per second, dx over dt. The rate of change is with respect to seconds, right? So the time is the denominator in our derivative as well as in our units. That's a good thing to keep in mind. If you're getting confused with what to take the derivative with respect to, you can always use the strategy. Look at the units. The units will make everything very clear. And we wrote our important points down, and we have established that we're trying to find dy over dt as it's going down. Now, what do we do next? Well, I already hinted what we're going to do when I said right triangle before, right? Yes. I think a good thing to keep in mind is the Pythagorean theorem. And let me tell you this, in calculus, unlike algebra or geometry, from something you've done before, it does not necessarily just refer to the unit from the past. It can refer to anything. So when you're doing calculus, creativity is the way to go. Now, I'm writing the Pythagorean theorem the standard way. And if you notice, we have all the variables we need in that equation itself. So we can directly take the derivative. And as I'm taking the derivative here, you can observe that there are three rates of change. But even though there are, in theory, one of them is actually zero. Can you identify which one? Well, if you said dl over dt, you would be correct. And the truth is, ladders do not change in size unless it's a special ladder from the fire truck or something, but that's not what we're doing here. So it's a regular ladder. So we only have two rates of change, and we already know one of them, so this is easy to solve. But unfortunately, in this problem, we still have something missing: our height. We don't know how high the ladder is, and we need to know that to solve for dy over dt, right? Because we have two unknowns now. But the good thing is, we can solve for y very easily. All we have to do is use the original Pythagorean theorem to figure out y, and use that to solve our equation to figure out dy over dt. Sometimes you're also given y without you needing to solve it. So keep in mind that questions can differ. Okay, so we have determined that y equals 8. So we know that the end point of the ladder is 8 feet tall. All we have to do now is plug y into our derivative equation, and then we get dy over dt. Okay, now I'm going to be rewriting the derivative from before, and after that, I will substitute in all the values we know, and then we can get dy over dt. So I'm substituting the variables we know already. So we know that the left side is going to be 0, and the right side is going to be having an x of 6 dx over dt of 1, dy over dt, something we still need to solve, but y is 8. So let's put everything in and solve for dy over dt. All right, so looks like we're getting dy over dt to be a negative 12 over 16, which I believe is going to be 0.8 or something. Oh, yeah, negative 0.75. But what this actually means is that the ladder is falling at negative 0.75 feet per second, or I should be saying it's traveling that. If we are talking about falling, it's going to be positive 0.75 feet per second. Direction matters. So if it's asking you the rate at which it's falling, you should be saying positive 0.75 feet per second. The rate at which it's traveling is going to be negative. So the negative in calculus, again, depends on your context. Most of the negatives you arrive at are contextual because rate usually deals with vectors.